Hi, y'all. This video is going to go back over talking about the mole and Avogadro's number, which was material that we did before Thanksgiving, and then get into some stoichiometry, which is what we did Thanksgiving week, and then we'll be working on after Thanksgiving. So hopefully, if you're having a hard time or if you're stuck at home in quarantine, hopefully this will help you clear some things up. So first thing I'm going to talk about is about the mole. Um, the mole is a measurement that chemists use that is based on information about the mass of atoms. So way back when, we don't have to worry about this so much since we don't have a final exam coming up. We talked about how we had a mass number, which was the number of protons plus the number of neutrons in an atom. And that was really close to the number on the periodic table down at the bottom, that decimal point number. When we found the average mass, which was the mass of all of the different isotopes of that element, we got that number. So we're going to keep using that number. We're not going to worry about atomic mass so much right now, but we're going to use that number on the periodic table to help us identify something that we figured out. So way back a long time ago, this dude named Avogadro was studying carbon-12, which is one of the isotopes of carbon. And he did a whole bunch of estimations about how many atoms existed in 12 grams of carbon-12. And he came up with this number of 6.02 times 10 to the 23. And so we as chemists have checked this number over and over again, now that we have much more technology than Avogadro had back hundreds of years ago. And he was right. And so we use this number, 6.02 times 10 to the 23, to identify the number of atoms in what we call as 1 mole. Mole is abbreviated MOL, which is totally safer than, saves you a ton of time from writing out that E. But so a mole acts just like a dozen. A dozen is 12. It could be 12 of anything, right? It could be 12 cars. It could be 12 people. It could be 12 donuts. It doesn't matter the size or the identity of that substance. It's just a counting number. So a mole works out the same way. A mole equals 6.02 times 10 to the 23 things. Doesn't matter what those things are. It's just a counting number. For our purposes, we're going to talk about it in terms of atoms when we have a single element, molecules when we have compounds, and every once in a while you're going to see the term formula unit. That's a fancy way of talking about molecules for only ionic compounds. So we can use Avogadro's number as a conversion factor to help us do some math. So if I have 1 mole of sodium chloride, we can also talk about molecules in terms of how many moles of each element they are made out of. So in 1 mole of sodium chloride, that is made up of 1 mole of sodium and 1 mole of chlorine. If I were to talk about MgCl2, magnesium chloride is made up of 1 mole of magnesium and 2 moles of chlorine. So that if I had 3 moles of magnesium chloride and I want to know just how much chlorine I had, it's twice as much because I've got 2 chlorines in there. Now we can use Avogadro's number if we're talking about molecules or atoms. So we're going to use a conversion factor. And so that 1 mole of anything is 6.02 times to the 23 things. That's our conversion factor. So I'm going to take the number that they gave me. You can put it over 1, so it looks like a fraction. That might help you out with your math. Notice that I've got moles of CO2 as the number that they gave me in the problem. Because I have moles of CO2 on top of this fraction, I need there to be moles of carbon dioxide on the bottom of my conversion factor so that those units are going to be able to cancel out. Just like in algebra, if there's something on top and on bottom of a fraction, they cancel each other out. So 1 mole of any chemical, doesn't matter, this is talking about in terms of carbon dioxide, has 6.02 times 10 to the 23 molecules of that chemical in it. So moles of CO2 and moles of CO2, just that unit cancels out. And then I'm going to multiply these just like I'm going to multiply fractions. I'm going to multiply all of the numerators, divide by anything that's a denominator. So 4 times 6.02 times 10 to the 23 gives me 2.41 times 10 to the 24th. I need a label of what unit I'm talking about. Now notice that that unit is the same unit that's left over from my work that didn't get canceled out. And I need a label of what chemical I'm talking about. That's going to come in really handy later. It's just good to get in the habit of doing it right now. So now on the second example, if I have 2.5 moles of CO2 and I want to find out how many atoms there are in there, I'm still going to start off with the number that they give me. I'm going to start off with that 2.5 moles of CO2. Again, since I have moles of CO2 on top, I need moles of CO2 on bottom of my conversion factor. I can always turn moles into molecules. So that moles of CO2 is going to cancel. If I stop there, I would have the same math as I did in this example up above, but this time they're asking me for atoms. Atoms are each individual element. So in CO2, I'm made up of 1 carbon and 2 oxygens, and so that means I have a total of 3 atoms in every 1 molecule of CO2. So again, molecules of CO2 and molecules of CO2, those units are going to cancel. So if I multiply all the numerators, divide by any of the denominators, I get 4.52 times 10 to the 24th total atoms in that carbon dioxide. So Avogadro's number can get used, push too many buttons. Avogadro's number can get used anytime we're talking about molecules or atoms in a substance. So here's a couple funnies. We also can talk about moles in terms of grams. So now this is really easy for us to recognize because grams is something that's easy for us to weigh out in the lab. And this is how Avogadro actually defined the mole in the first place. So he said a mole is equal to the number of atoms in 12 grams of carbon-12. And if you look on the periodic table, the average mass of carbon on the periodic table says 12.01 grams. So we found a little bit more accuracy in that number than when Avogadro was doing this math, but that's where that number comes from. And so that decimal point number on the bottom of each square of the periodic table, we're also going to call either the molecular mass or the molar mass. So if you look up sodium, sodium's molar mass is 22.99 off the periodic table. The unit on that is going to be grams per mole, because what that number is telling me is that sodium weighs 22.99 grams for every 1 mole of sodium you can weigh out. Carbon, again, is 12.01 grams per mole. Silver, 107.87 grams per mole. So that one is a little bit heavier. When we have a molecule, such as sodium chloride, we're going to go to the periodic table. We're going to add up the masses of each element in that compound. So sodium chloride is sodium, which is 22.99, plus chlorine, which is 35.45, gives me a total of 58.44 grams per mole. Now, if you notice on your periodic table, there's a couple elements, several elements actually, that go to an outrageous number of decimal points. For our purposes, we're only going to round molar masses off to 2 decimal points because that's really as accurate as we need to be. So water, again, as a molecule, it's got 2 hydrogens plus 1 oxygen. So if I add up 2 hydrogens, each is 1.01, oxygen is 16.00, gives me a molar mass of 18.02 grams per mole. Sodium phosphate, Na3PO4, I need to add up 3 sodiums, 1 phosphorus, and 4 oxygens, gives me an overall molar mass for sodium phosphate of 163.94 grams per mole. Now, that molar mass that we get from the periodic table, we can use that as a conversion factor as well, because it is grams per 1 mole. So if I have sodium nitrate, it says how many moles of sodium nitrate are in 308.25 grams. So if I start with the number that they give me, 308.25 grams, put that over 1. Again, I've got grams of sodium nitrate up here, means I need grams of sodium nitrate down here. So I can use my molar mass as this conversion factor. I go to the periodic table, add up 1 sodium, 1 nitrogen, and 3 oxygens, and I get 85 grams. Now that's 85 grams for every 1 mole of sodium nitrate. So multiply across the top, divide by anything that's on the bottom. we should, I didn't do a very good job, but we should think about sig figs. So 3.63 moles of sodium nitrate. Notice again, I've got moles, which is my unit, and I've got my label of what chemical I'm talking about. The grams of sodium nitrate cancels out. That's the same unit as I've got left in my math. We can combine our idea of being able to break that molecule up. So if I have that many moles of sodium nitrate, in 1 mole of sodium nitrate, I would have 3 moles of oxygen. Because of that subscript 3, it tells me I've got 3 of them. So I can convert that into moles of just oxygen if I need to also. Go in the opposite direction. If I start off with moles, if I've got moles of sodium chloride as my given number, I need moles of sodium chloride to be on the bottom of my conversion factor. Then I can put grams on top, moles of sodium chloride and moles of sodium chloride. That unit is going to cancel. That would leave me with grams of sodium chloride. So again, we calculate that number right off the periodic table. This time they're asking for kilograms, so we need to convert that grams into kilograms. And we can actually get both grams and molecules or atoms into the same calculation. We can use both of those conversion factors to get from one measurement to another measurement. So for example, here we've got how many molecules of water are in 20 grams. So as always, I start with the number that they give me in the problem. So I'm going to have 20 grams of water. I can convert grams of water, put grams of water on the bottom of my conversion. I can convert that into moles using my molar mass. So grams of H2 and grams of H2 are going to cancel, but they want me to get to molecules. So I'm going to add a second conversion factor onto here. If I've got moles of H2 up here, I need moles of H2 to be on the bottom of my conversion factor. So I can see that that moles, I can then change that into molecules. So that unit is going to cancel out. My final units are going to be molecules of H2. So if you notice, the whole time we're doing this, we're really letting those units guide where our math is going to be. You really need to write out all of your work this way. You need to follow this pattern. I know that sometimes people look at this and go, well, I know I just need to divide by this and multiply by this. But the chances of making mistakes when you do it that way are pretty high. So make sure that you're writing out those units, that you're following along with your work, that you're showing all of those conversion factors as you work all the way through this. Where this idea of the mole takes us next is to something called stoichiometry, which is a really fun word to say. It's one of my favorite chemistry words. Stoichiometry means, if we break it down into the Greek words and roots that it means, stoichiometry is literally the measuring of particles, which is what we're going to do. We're going to keep track of all of our particles in a chemical reaction now. So we're going to be talking about something that is reacting. We're going to have balanced chemical equations, and we're going to be able to talk about what is our reactants, what is our products, and what's going on with all of that. So chemical reactions work out the exact same way as recipes. So if we have a recipe, this recipe is for chocolate chip cookies. Recipes usually tell you how much of each ingredient you need, usually in different units, cups, tablespoons, teaspoons, count numbers like 2 eggs. And then it will tell you how much of your recipe it will make. For this cookie recipe, it says it makes 5 dozen cookies. For another recipe, it might say serves so many people. Chemical reactions really work out the exact same way. They tell you how much ingredients you need to put in as your reactants, and then they tell you how much products or how many cookies you're going to get out at the end. And so we can use those ratios to figure out some other things. So if one batch of cookies, one batch of this recipe requires 2 eggs, and I look in my fridge and I have 5 eggs, and I know that I have plenty of all of my other ingredients, how many cookies can I make? Well, I know that if I double my recipe, I'm going to need 4 eggs. So 2.5 times this recipe is going to use up my 5 eggs. If I have 5 eggs, I start off with 5 eggs. I know that 2 eggs is going to get me 5 dozen cookies. 5 times 5 gives me 25, divided by 2 means that I can get out 12.5 dozen cookies. So I can use a conversion factor from my recipe, just like I was using conversion factors for my molar mass or for Avogadro's number earlier. So we're going to use what we call the mole ratio, which is the ratio that we get from our recipe or from our balanced chemical equation. So the coefficients in front of our reactants and products tell us our mole ratio for a balanced equation. So this chemical equation on the screen says that 2 moles of magnesium react with 1 mole of oxygen to make 2 moles of magnesium oxide. So using that ratio, I can figure out, well, if I start off with this much magnesium, how much magnesium oxide can I get out? Or if I have this much magnesium, how much oxygen do I need to react with it? So it's really just a recipe, again, telling us what to do. So anytime we're doing any of this, we need to make sure that we have a balanced equation. In your packet, there are several questions that tell you what's happening in the words, but they don't write out the balanced equation for you. So you will have to write out that balanced equation from the problem itself. Always see what number they're giving you, what's the known, and what the unknown is, where they want you to get to as a product. Line up your conversion factors using those units to guide you. If we have a mole ratio, that's going to get from moles of one chemical to moles of a different chemical. And we're also going to be using molar mass a bunch. So relating how many grams there are for 1 mole of that chemical. Molarity, we're not going to see a whole lot here. We might see a couple about molar volume, which we'll talk about in just a second, which connects moles to liters. But that mole ratio, using those coefficients from our balanced equation, that is going to be in every single stoichiometry problem we ever do. Right? So if they ask you to convert to volume or liters, we have an extra conversion factor we can use. We can say that 1 mole of any gas is going to have a volume of 22.4 liters. So we can use that as a conversion factor to connect moles to liters. Instead of this picture, I want to take a look at this one instead. I call this the mole highway. And so this is sort of a nice picture, and this is up on Schoology for you guys to show the path that we can take depending on what's given to us in the problem and what they're asking us to find. So the things that we could start with are all over here on this side. We could start with molecules of a chemical. We could start with liters of a chemical. We could start with grams of chemical, or we could start with moles of a chemical. What they're asking us to find or what the unknown is could be any of these things on this side. We could ask to end with moles or molecules or liters or grams. So it's all the same measurements, but it's just how we get there. And notice here in the middle, there's that magical step that we're always going to be using, which is that mole ratio of that ratio coefficients from our balanced equation. So let's try out a problem. So this problem says, how many moles of KClO3 must decompose in order to produce 9 moles of oxygen gas? So the very first thing we have to do before we do anything else is we need to get a balanced equation. So we say KClO3 must decompose in order to produce oxygen gas. So if I've got KClO3 decomposing means breaking apart. If it makes oxygen gas, remember oxygen is a diatomic element, so it's going to be O2 and not just O. The only thing left over is the KCl. Now that's a kind of a tricky one. They probably, if I ask you to do this on a quiz or anything, I'm going to tell you what all of the reactants and all the problems are. You just might have to write the formulas from the words. So then I need to look at it balancing. If I've got 3 oxygens on this side and only 2 oxygens on this side, the only way to make that balance out is to have 6 oxygens. So I put a coefficient of 2 here and a coefficient of 3. Then I need to balance out my potassiums and my chlorines, and to do that, I need a 2 in front of that KCl. So now that I've got my balanced equation, I can start with the work that I need to put in here. So I look at the problem and I see what we're starting with. We're starting with 9 moles of oxygen gas. So 9 moles of oxygen gas is what I'm going to start with. You can put it over 1 if you need to. I like to use this long line. This process of doing math this way is called dimensional analysis. I like to use the long line because my writing tends to get a little messy, and that helps me remember what my numerator and my denominators are. You also could just write this as a fraction with a multiplication sign there. That would be totally fine. So I start with the number that they're giving me. I need to figure out where I'm trying to get to. I'm trying to get to moles of KClO3. So if I look at my mole highway and get rid of all my writing, I am starting off with moles, and I'm trying to get to moles of a different chemical. So this is going to be a one-step stoichiometry. All I need to use is my coefficients and that mole ratio to get me there. So again, just like before, if I've got moles of O2 up top, I need moles of O2 on the bottom of my conversion so that those units can cancel. And I'm trying to get to moles of KClO3. So moles of KClO3 goes on top. Now the numbers that go here, all I have to do is just copy down the coefficients that are in my balanced equation. So if I've got KClO3 on top, the coefficient with KClO3 was a 2. I've got oxygen down on the bottom. The coefficient that goes with oxygen is 3. So same work. I got moles of O2, cancels with moles of O2. The unit that's left over is moles of KClO3. That's what they wanted me to find. So I know my work is done and I just need to algebra it. So 9 times 2 divided by 3. 9 times 2 is 18. Divided by 3 gets me 6. Right? So here's another one. How many grams of potassium chloride are required to produce 9 liters of oxygen at STP? Now this is going to be more than one step. So again, I need my balanced equation. It's the same equation as we used in the problem before. They're asking me to find grams of KClO3, and I'm starting off with 9 liters of oxygen. So I go back to my mole highway. I started with liters, and I want to get to grams. So this is going to require a couple more steps. So first step is I need to get liters to moles. So I can start off with the liters that are given to me, 9.00 liters of O2. If I've got liters on top, liters has to go on the bottom. Again, my 3 choices are either using molar mass, which has grams, using my mole ratio, which is moles to moles when I'm talking about changing from one chemical to another, or using that volume conversion that we talked about earlier. So I'm going to say that 22.4 liters goes to 1 mole of oxygen. That's the only way to use liters in a conversion at all. All right, so now liters of O2 and liters of O2 cancel. If I stopped my math right here, my answer would come out as moles of O2. That's not what we want. We want grams of KClO3. So now that I've got moles of O2 needs to go on the bottom down here. I need to start talking about KClO3 because that's what my answer needs to be at, not oxygen. This is why making sure the labels in your work are so important. So if I want to go from moles of O2 to moles of KClO3, if I look at my mole highway, now I'm doing this step of going from moles of one chemical to moles of another chemical using my mole ratio. So based on my balanced equation, 2 goes here with KClO3 because that's the coefficient there. And then oxygen gets coefficient of 3. I'm going to run out of room, aren't I? Moles of O2 and moles of O2 are going to cancel for units. If I stopped there, my answer would be in moles of KClO3. I need grams of KClO3. So now that I got moles up here, I need moles of KClO3 to go on the bottom so that that can cancel. And to turn that into grams, I need to find the molar mass of KClO3. So I go to my periodic table, I add up 1 potassium, 1 chlorine, and 3 oxygens. And I don't have a periodic table in front of me, so I'm going to depend on my PowerPoint to tell me what the answer should be. Okay, so that's what we had. 122.55 units of moles of KClO3 cancels out. Now my unit that's left is grams of KClO3. That's what I want my answer to be in, so I know that I've set my work up correct. So I'm going to take 9 times 2 times 122.55 divided by 22.4 and divided by 3 gives me a total of 32.8 grams of KClO3. So if we take a look at what we did here, we've got the number we started with. We have one conversion factor that's always the same as long as we're talking about liters. We've got a conversion factor for our mole ratio using our coefficients from our balanced equation. And we've got a conversion factor using mass, the molar mass from the periodic table. So if we use those steps on our mole highway, we're always going to get to where we need to go. So 3 steps is really sort of the maximum. Every once in a while, we might throw something weird in there where we could get more than 3 steps. But in general, 3 steps is about as long as we're going to get. So if you follow along either with this mole highway, or if you write yourself some notes about what conversion factors to use when, that's really going to help guide you to the right answer. I really hope that that has helped clear some things up. If you still have any questions, please feel free to reach out to me, and I will help you as much as I can. Remember to let those units guide you on your way. Write out all of your work to make sure you're doing things in the right order. And that should get you 90% of the way there. I will talk to y'all later. Bye.